Okay. Uh, in this discussion, we're going to continue to talk about some basics of linear model, which is this model that we defined earlier, where we have the epsilon following a normal with zero mean and the identity as covariance matrix. And we also have that the distribution for y is x beta with epsilon identity. So same covariance, constants variance. Okay, so now let's talk about some other, you can say, property of the linear model. So let's first look at the y hat, the covariance of y hat and the residual. So here we're going to define, or maybe I'll use y hat is essentially x multiplied by x beta. This is x multiplied by x transpose x inverse x transpose y. The solution that we find from the previous discussion. And now we are going to group these parts. And we define as h multiplied by y. And this h is what we call the hat matrix. Then just adding a hat and then referring to the predicted y values that is coming from our estimated coefficient multiplied by data. And similarly, residual is y minus y hat. This is just identity minus h multiplied by y. So all of these details can be found in the previous discussion. Now let's write the things that we define here. H multiplied by y, I minus h multiplied by y. Okay, so let's call this as A, let's call this as a matrix B. So another side note, covariance of AX and BY. Here just referring to any vectors, random variables. This is equal to A covariance of X and Y. So covariance of two random variable and then B transpose. Just one another rules that we can use. And we're going to apply the same thing here. Okay, so we're going to call that as A and B. And that is equal to H covariance of Y and Y, the two random variable, I minus H transpose. And here, covariance of y and y is just the variance matrix of y. So it's just sigma square identity dimension n. And we have h here and I minus h. Previously, we mentioned that I minus h or h is symmetric and idempotent. So h, the transpose here can be cancelled out. And we just have sigma square h minus h. One copy of h, and then idempotent is referring to h multiplied by h is equal to h. You can expand the h with this, and then you will see that it will cancel out into one copy of that, and that is idempotent. And that makes it 0. So that's one equation or one relationship that we can find by looking at the covariance of that. The second quantity that we are going to talk about is the covariance of beta hat and the residual. So here, let's plug in This is just the closed form solution for beta. And then I minus h multiplied by y. Okay, so same thing. X transpose X inverse X transpose. And then covariance of y and y. So here I'm just going to put sigma identity for the variance of y and y. I minus h transpose. Symmetric and idempotent, so I'm just now going to put the transpose here. Sigma square in the front as a scalar. X transpose X inverse X transpose multiplied by identity minus X transpose X inverse X transpose. And then here we are going to write the H matrix explicitly. Two copy of that cancel out. Have sigma square X transpose X inverse X transpose minus the same thing. We have another equation here, covariance of that equal to 0. So the covariance of your prediction and the residual are 0, and the covariance of your estimated coefficient and residual are also 0. Let's comment on another thing. Let's take a look at the covariance of y hat and beta hat. This is maybe I'll just use this setup here. H multiplied by y by adding a hat to the true value. And here I'm going to use the X transpose X inverse X transpose Y. Let's further bring H to the front, sigma square identity. This matrix, let's denote as B. We need the B transpose here, so I'm going to write X transpose transpose, so it's just X itself, and then X transpose X inverse. This is symmetric, so the transpose of this entire inverse is also just itself. Sigma square in the front, and then we can write H explicitly. So this part is the H, and let's continue the matrix B here, the B transpose. Okay, so you can see that some of the term can be cancelled, but not all of them. So we have that. Let's use the X here, and then so here we just comment that the covariance of the prediction and your residual are 0, and the covariance of your estimated coefficient and the residual are 0. But the covariance of your estimated prediction and your estimated coefficient is not 0. Okay, so here are just 3 equations that we can comment on that. And later, we will use some of the relationship here to further to proceed our analysis. Okay, some of the side notes here you can find from the previous discussion. Okay, next we want to talk about basically it's hypothesis testing on beta I. So remember that beta is referring to your coefficient p by 1. Here, when we conduct the t-test, you can only test on one of the coefficient. So this is referring to the hypothesis, not the H matrix. So beta I not equal, say, equal to a particular value. Maybe you just put 0. Usually we're just interested whether it's 0 or not. And your alternative is not 0. So we're going to perform this kind of test. But in order to do that, we need to talk about the distribution for this. And it actually following a t distribution. So we need to, so the next is just we need to derive this conclusion here. Okay, so in order to conduct the hypothesis testing for a particular, the beta for a particular column or feature, it's actually the t-test, and we are going to derive the t distribution, which is coming from a standard normal over a chi-square. And here I'm just going to write a degree of freedom p n minus p for just for a placeholder. And later we will talk about where the n minus p come from. So if we are able to construct a test, able to construct a random variable having this form, this is following a t distribution with degree of freedom n minus p. Okay, so that would be the high-level idea. Next, we're going to talk about that. First of all, here I'm just going to borrow the assumption, the distributional assumption that we have so far. Y is a multivariate normal, n by 1. Okay, and y minus x beta. Let's standardize it. So -1/2. And then here we have it follow a normal mean 0 identity n. Okay, so we are just standardize it from a general normal to a standard normal. So this is equivalent to usually what we have plus mu, that is equal to x, and x follow a mean. This is just for a univariate case, but this is just a reparameterization tricks that we do here. And then, yeah, so you have z is equal to x minus mu over sigma. This is essentially what we're doing here. Y minus the mean vector over sigma, except here we're just talking about matrix, so you need the 1/2 power for a matrix here. Okay. So after the transformation, we have that. Similarly, we also have beta hat following a normal distribution centered around the true beta and the sigma square x transpose x inverse. This is all coming from the previous discussion, so you can refer that for details. Then similarly, we have sigma square x transpose x maybe I just for notation simplicity, standard deviation after we take the 1/2. Maybe I'll just put 1 over that, so the negative here, and then the 1/2. One over sigma. And we have x transpose x 1/2. So the inverse and the inverse cancel out, but we still have a power of 1/2 here. So this is just referring to sigma square x transpose x inverse, and all of this negative 1/2 to construct the standardization here. But after simplification, we have the negative sign to make it 1 over sigma. 1/2 and the square cancel out, and then the 1/2 remain, but the negative sign cancel out. Beta hat minus beta, following a normal. Here, the dimension for the matrix is P, because this is a P-dimensional vector. Okay, so this is giving, after standardization, we have this standard normal distribution, and this is coming from here. Okay, so from this normal distribution, standardize it, we have that. Okay, and then these two normal, standardized normal is the two distributions that we're going to use later. Okay, with that in mind, let's discuss how we are going to verify the distribution for beta as a t distribution, and to conduct our hypothesis testing. So let's start from y minus x beta. And here we are going to starting from this equation over sigma square. Okay, coming back from here, maybe we can also simplify here just for notational simplicity. So we have the 1/2 and the sigma square cancel out, and then it becomes a fraction. So same as this one. And what we have here is essentially taking a square. So we have one copy of y minus x beta over sigma, and we multiply by another copy of 1 over that y minus the mean. So essentially, this is actually a chi-square distribution with degree of freedom n. We have a vector, each of them following a normal. And here we're taking a square and then taking an inner product. That is equivalent of each of the standard raised to the power of 2, sum them together. We have n copy of them. So n copy of zi square. This is equivalent to a chi-square distribution, degree of freedom n. This is just a definition. Chi-square can be constructed by taking the square of a standard normal random variable and then sum. If we have n copy of IID samples, then you will have a chi-square degree of freedom n. And here we also have the IID assumption here, where the y each of the observation, each row is independent to any other rows. So we have that identity IID assumptions. So that will give us a chi-square distribution, degree of freedom n, for this summation. Okay. So we know that the left-hand side having a chi-square degree of freedom n. Next, we're going to elaborate on this on the left-hand side. So y minus x beta, and then we're going to plus x beta hat minus x beta hat. Okay, so it does not change the quantity, but we introducing new notation here by introducing the one that we have. Okay. So let's further simplify from here. Plus one copy of x beta hat, and then plus x of beta hat minus the true beta. So this copy coming from here, and then beta hat minus beta. Taking the transpose and then same procedures here. So far we do not change any quantity here. So the equal sign still holds. Now let's just factorize the terms. E transpose E sigma square plus 2 copy of E transpose x beta hat minus beta sigma square. So that's that, and we also have E transpose X and beta hat plus beta hat minus beta transpose X transpose X beta hat minus beta over sigma square. So we are just expanding the square term on the numerator. Just double check. 2 copy of that, 2 copy of E multiplied by that. Okay. One thing to comment, so maybe this is a fourth equation that we can get. Let's see. I think this is I minus H. So we have y transpose I minus h multiplied by x. So here I'm just writing the E as I minus h multiplied by y, but we have a transpose here. And we have y transpose x minus h x. And then h is just x transpose x inverse x transpose multiplied by x. Let me y transpose, and then x minus, and then let's bring in the H matrix here. So this is the H multiplied by an extra copy of X. So as you can see that there's only these two can be cancelled out. So we have one copy of X inside the parenthesis. So it becomes a 0. So that will give us this quantity equal to 0 because involving a E transpose X. E transpose X. They all become 0. Okay, so this is another quantity that we can use here. So what we have done so far is that we're starting from a chi-square distribution, degree of freedom n, and we decompose to something on the right-hand side. So only two terms remaining here that is not 0. Okay, so let me just write it again. This is what we start from. This is the true value for the beta over the sigma square, which we known is a chi-square degree of freedom n, with a E transpose E over sigma square plus beta hat minus beta x transpose x. There's no inverse here. And then beta hat minus beta over that. So the question is, what is the distribution for this? And we have actually seen this earlier, which is coming from here. So we have that is a standardization for a p-dimensional multivariate normal. And what we have done in the bottom is that we take the square of this. So we have there's a transpose here. So we have two copies of that. Essentially. This is 1/2 and then 1 over sigma. This is a p-dimensional normal. And here we're just taking the square by having two copies of that, so the 1/2 cancel out, left and right multiply of a difference. So this is essentially chi-square with degree of freedom p. So after we standardize it, we see that they are not they are independent because we have identity covariance matrix. And then when we sum them together by using the inner product, it becomes a square of a standard normal, and we have p copy of them, so it becomes a chi-square degree of freedom p. Okay. So this is all the information that we know so far. And now the next question is, what is the degree of distribution for that? Okay, so now we are going to use the the funding that we have from here. We know that the covariance of your estimation and the residual have a covariance of 0. So that means this random variable and this random variable is independent. And we also know that the residual, so basically these two random variables are independent. And then we have a chi-square distribution here and then a chi-square distribution of here. So here we're going to use the moment-generating function for two random variables, and then if they are independent, this is equivalent to the product of the moment-generating function. And chi-square distribution is actually a special case of a gamma distribution. So the moment-generating function for the left-hand side is 1 minus, okay. So chi-square distribution is a special case of a gamma distribution. So we have the gamma distribution as n over 2. So this is the alpha and the beta. So this is the moment-generating function for a gamma distribution. Negative alpha. Okay. And that gives us 1 minus 2t negative n over 2. Multiply by the equal to the moment-generating function of residual, which is something that we don't know so far. Multiply by 1 minus 2t. Here is a p-dimensional chi-square, a degree of freedom p. So we have that. And because we know that they are independent based on the covariance that we get earlier, so finally we have the moment-generating function for the residual, or actually it's the E transpose E is 1 minus 2t negative n over 2 over the other moment-generating function of a gamma distribution with alpha equal to here. This is p over 2. Okay. And then we will have 1 minus 2t n minus p over 2. So because of the uniqueness theorems, we know that the actually this is entire random variable. So this random variable also have a chi-square gamma distribution of n minus p over 2. And this is essentially a chi-square distribution. Degree of freedom n minus p. Okay. So because the covariance of E and the beta hat are independent, and we know that both the left-hand side follow a chi-square distribution, degree of freedom n, and this follow a chi-square distribution, degree of freedom p. And we use the moment-generating function of the two gamma distribution, taking the ratio, because they're independent, so that you can they're equal to the product. And we have our final conclusion that this thing follow a chi-square distribution with degree of freedom n minus p based on the uniqueness theorems of the moment-generating function. Okay, so up to this point, what we have is the distribution for that. But our final goal is to conduct a hypothesis testing for a particular beta I. So next we're going to make the final connection between the chi-square that we found with that to construct a t-distribution. So first of all, we need to comment that beta hat follow a normal with that covariance. Here we're just going to use a vector which is all zeros except that the ith index it's a 1 multiplied by beta 1 to beta I to beta P. So this will give us beta I. But this is a linear transformation of a random variable that follow a normal. A transpose beta. A sigma A. So for a vector, we put the transpose in the front. And then A. So this gives us essentially the I beta is also a normal distribution with the ith true value for beta, but sigma square. So here let's denote a matrix P by P as X transpose X inverse. And after we take the products of A vector A, which is this one, multiplied by sigma V and A. This is essentially the matrix V and then the ith elements. Okay, and this is referring to the variance covariance matrix. So when we take the product of the vector A, left and right multiply, we are extracting only the ith elements of this particular matrix here. So I'm going to use V to represent it. Okay. So each of the individual elements for the estimated coefficient also follow a normal distribution and with this particular variance. So here, this is a scalar. Everything is a scalar now. Okay, so that's that. Now we are able to talk about the test hypothesis for a particular beta I over sigma VII square root. So this is a standardization. So it becomes a normal 0, 1. This is a scalar. But what we usually don't know is the estimation for the variance. This is what we don't observe. So that's why we need to use t-distribution to look into that. And we have this E transpose E sigma square, which we know is a chi-squared degree of freedom n minus p. And then divided by its degree of freedom, taking the square root. And we have chi-squared degree of freedom n minus p minus n minus p. And this fraction altogether is the definition for t-distribution. So if you are able to construct a random variable with this form, this is a t-distribution degree of freedom n minus p. Okay, and then from here you can see that beta I, here I'm just going to say our null hypothesis is beta I equal to 0. So I'm just going to minus 0 for this particular test. And then this sigma square and this sigma squares cancel out. So we only have over this matrix. And this matrix can be obtained from your data. And we have E transpose E. This can also be obtained from the difference of your true and your predicted value minus n minus p. This is the number of observation minus the number of parameters including the intercept. So everything here after simplification can be obtained from your data. And then you can use the t to perform your task for this quantity. And this is equivalent to performing a task for a particular coefficient equal to a particular value. Here I'm just using 0 for this test. Okay, and everything should be able to obtain from data or is known information. And the reason for that is that if we know the true sigma or sigma square, then we are able just to use the normal distribution to perform the task. But usually we don't know, so we need to estimate that. By estimating the variance here, then it's no longer a normal distribution. It has to be a t-distribution, and then with this degree of freedom. And yeah, so here we have our basic test, or our reasoning for this, for the setup for this hypothesis testing. And now we are going to perform in R just to double check. So here we have our x and y, and this is the result from the built-in function in R. We have the coefficient estimate and also the individual test for each of the coefficients. So here we have the t values. And now we are just going to use the same solution that we derived. So this is the x transpose x inverse x transpose y, our closed form solution for beta. And first of all, we can see that our closed form solution is exactly the same as the built-in function that we get from R. This is the E that we get. And here's the V matrix. So make sure that you need to take the inverse of all the features together. So x transpose x first, take the inverse to get your V matrix. And the numerator is that we're conducting the test for beta equal to 0, and then divided by the square root of the matrix V for the ith entry. Here I'm just going to use the 2 entry here. So this is referring to the first element, the first coefficient that is not the intercept. That's the numerator, and then the denominator for E transpose E over n minus p. Including the intercept, we have 20 coefficients here. So that's the denominator. And when you take the numerator over the denominator, that should give you the t statistics. And we have that equal to negative 3.12. And let's take a look at the summary from the built-in function. and then it also give us the same t statistics here. And then from here, you can consult a t table, and then to find the probability from that, and then you can decide whether you want to reject or not reject your null hypothesis for this particular test. And then if you have a different numbers here, then you need to make sure you minus that as well. Okay, so in this discussion, we just basically covered our derivation for the distribution and how to perform the t-statistics or hypothesis testing for an individual coefficient. And then you can perform like 20 individual t-statistics to test each of the coefficient, whether it equal to 0 or not, or equal to a particular value. And yeah, so that should conclude our discussion today.